Well, we're talking, as you recall, about multiphase flow as part of the question of how fluids travel in the subsurface. This, I think, is an interesting video. You could imagine this if it was turned on its turned 90 degrees and was vertical. This is just oil and water and flowing within a porous medium. You can kind of see the grain outlines. You can see the blobs of the fluids going through. I think the color scheme are that the blue is low pressure, from high to low pressure. High pressure on the left-hand side red, and blue on the right low. But these are little blobs that break off and behave in some interesting way within the system. And that's physically what we've been talking about, albeit that we were interested in talking about it in a very simple way. What we've talked about so far has been these capillary pressure versus saturation diagrams. And they don't say anything about the rate at which this flows through the system. It talks about some equilibrium architecture, if you like, of the oil and the water and the gas within the system, and how it would come to rest in that configuration. And then we can worry about what goes on if we then change the boundary conditions to actually push it through. So far we're not doing anything as sophisticated as this to look at the rates at which it travels. We're just saying it can travel, and it ultimately gets hung up by capillary forces and then can't move. And that's good, because then we can choose to either remediate it, or if it stays there, it only dissolves at a very slow rate, and maybe it's not such a big problem in the subsurface, although that's not quite true. I wish this would loop continuously. I don't think you can do that necessarily on YouTube. Maybe you can. You probably know better than I. But this is actually an interesting company. It's set up not to do things in groundwater hydrology, but it's now been bought out by Halliburton. It's in the area where fluids are a bit more valuable than water. Water is very valuable, but petroleum hydrocarbons are a bit more valuable. I remember I work in geothermal energy, and I remember working out that a barrel of hot water at 200 degrees centigrade is worth about 25 cents. And so if you look at that value versus a barrel of oil, $50 a barrel right now, is why renewable energy has not quite broken through the marketplace as much as hydrocarbon, which obviously fuels our current economy, fossil fuels. But this is an interesting company in that the idea of it is that when you drill wells, you drill, and typically in the return drilling fluid you get chips of the reservoir, nothing very coherent, but small chips, maybe the size of your pinky thumbnail or fingernail. And what you could do with those is you could CAT scan them to look at the porosity, to get the outline of these grains here. We've always worked with idealized geometries. And then if you know what the porous architecture is, then you can run a model. These are lattice gas Boltzmann models to be able to look at what the transmission characteristics and the capillary characteristics of those porous media with very fine pores would be. And if you know that, then by extension you can say something about the behavior of an aquifer at a much larger scale. And so it's the idea that you can take these small samples, it's all you actually recover from the reservoir, get very accurate predictions of what the porosity distribution is, and you can come up with little models like this that would say, one, if you push these non-aqueous fluids into them, what their distribution would be, and two, if you keep on pushing them through, it would say something about the permeability of it as well. And so you'd know something about your reservoir. So a very clever idea. One of my colleagues here, Rami Grader, left to join them in this. It was a startup, and I presume he's probably going to do very well in life as a result of that. I think they play a bit more than universities, and it's an interesting area. Okay, so that's kind of where we are going with this. I did repair my tablet from last time, so it actually works. This outline for what we'll do today, actually it's not very close to what we'll do, as it turns out, but we will try and answer a couple of different questions. And the primary questions that we'll try and answer is, if I get this right, it was working. is that we'd like to know how non-aqueous phase liquids move in the subsurface. For instance, one question is, how deep do they go? Do they stop at some depth and not go any further? What are the controls by which that would occur? And also, in addition to this invasion, which is what we'll talk about, invasion, yes or no, which is kind of a binary thing. But also the other question would be, what's their architecture and their distribution with depth? And so that's not badly illustrated by this figure, which we had, this is it here, which I'll use here. And we've seen this a number of times, right? This geometry. These different architectures that we have for a NAPL, zips across the water table. It's stopped by an aquitard for sure, because it can't get into the pore space. If it meets some low permeability lenses that have small pore spaces on the way down, then it gets hung up on these and builds puddles on top of them that leak off either sides. If it's a smaller amount of a spill, then there's not enough maybe to go all the way down to the base. And if it's really heterogeneous, then it might have all of these different stacks of layers in the system. And in microcosm, what this looks like is that a particular portion of this, I suppose, if we would draw, it's a bit big for this, if we look at actually a little zone like this, let me do that backwards. If we look at this, say, I should have used something other than red. Let's say we look at a box that looks like this. Then this geometry is not all that different from this. You remember we explained that this, I should get a different color, shouldn't I? Is that along this boundary here is a boundary between these pretty big grains and these relatively smaller grains. The result of this is, that we're interested in, is the fact that the pore spaces in the lower part are smaller, and therefore this has got a very high saturation. So if you looked, for instance, in this and looked at what the saturation was, then the saturation of this non-wetting fluid might be about 100% filling the pore space, maybe a bit of water, which is present on the grain-grain contacts, but not much otherwise. If we go down here and do the same, and look on average at what the saturation would be, then if it's nearly 100% saturated in the little pathways that are filled, and zero non-aqueous fluid filled in the other parts, then the saturation in this might be of, I don't know, a half, just by the area proportions. Which means that the water saturation, if it indeed is water filled, would be the other half, because we know that together these have to add to unity. And so what we've done so far in looking at the systems, and I'll recap it in a big picture in a second, is to understand what are the controls on this and how we can explain this or describe this in terms of saturations. And so what I really wanted to do is kind of just quickly recap the path that we've taken, because I think it's important to do because it sets you up in making the understanding that we've got so far. And so the point that we started off with is, if we're looking at capillary behavior. Okay, I didn't want to do that. I guess it's big because it's magnified. That's why it's big. So anyway. I suppose it doesn't need to be so big because it's, so I can do this, yeah, right. So, and so the idea has been simply that two approaches that we can take has been to look at the behavior in a capillary tube and multiple bundles of them, or to look at grain to grain contacts, where we can look at how the fluids, the non-wetting fluids, arrange themselves. We can talk in this particular case about where a meniscus would go to based on the height of the capillary. And we can also talk about, that's not a very good bracket, is it? Trying to do a bracket. Combining these to be able to say something about what happens if you have capillary tubes that are either in parallel of different sizes like you have above, and also if they are in kind of series where you have a wide capillary tube followed by a narrow capillary tube. And we made the case that because the height rise in these narrow tubes is larger, that means that the entry pressures into these smaller capillary tubes would be smaller. And so any fluid that we might have that travels in these systems would get perhaps hung up in these narrow capillaries and then not go any further, as opposed to the case where these big capillaries here would just allow it to go straight through. And that's kind of our important conceptual point. And so we decided that this is kind of not a bad model to be able to understand in broad sense what's going on, but what would be better is if we could do experiments on real porous media, which would allow us to develop these particular capillary pressure versus saturation curves. And so let's just go back to that and define all of the features on one of those curves that are important to us. If I can try and that kind of sets the stage for what we'll do today. If I can do this. And I just want to talk about the ordinates that we described last time and what those mean. So you recall that this defines the saturation of the fluid. So the wetting fluid between 0 and 100%. If it's the saturation of the non-wetting fluid, it's the opposite. It's between 0 and 100%. We describe this as a drainage curve. Let me not do that. Let me actually put the axes on here. This is capillary pressure. Which we call PC, which is the difference between the non-wetting and the wetting pressure. We define this as a drying curve because it's drying, the water is drying. And we describe this as an imbibition. Which is this one here and this. We defined the non-wetting fluid. Of the non-wetting fluid. Which we'll refer to as SNW0 for obvious reasons. And the irreducible saturation of the wetting fluid, which we refer to as saturation of the wetting fluid, SW0. And that's this. And we talked about what those mean. So it means that if we try and push a bubble of oil into the system from zero saturation, we go up this curve, but this curve ultimately goes almost vertically upwards, and that's the level at which we can't get any more oil into the system because the water that's left in the system won't come out. It's stuck to the grain-on-grain contacts as this pendular saturation and as a monolayer covering of the grains, and this is the minimum amount of water saturation we get. If we then allow the pressure to drop, we'll come down this curve. It will freely give up the oil if there's water around it, and it will suck the water in, but it will only suck the water in up to this amount because the rest is left as this amount of oil that's left in the system. Any point on this in this graph, I guess, for instance, if we take just a random point, any point on this graph we can define as the saturation of water and as the saturation of the non-wetting fluid. I'm presuming, yeah, you can see that, it's quite big. And we know also from this that, maybe not there, maybe here, we know that SW plus SNW equals 1. Not the irreducible saturations, but any particular saturations of them. And that's shown by the fact that if you add these two arrows together, they're the full width of our curve. And so this just defines the behavior, the equilibrium behavior at any particular pressure between 0, I guess this would be gauge pressure. It doesn't have to be, it can be anything. And a high pressure. I don't know how to do that other than talk about high. And so those are the key features. I guess one other one, what else did we talk about? We talked about this pressure here. This was what we call the bubbling pressure. Or the entry pressure. So we're defining this as a precursor to be able to talk about, one, when does breakthrough happen and what's the distribution of saturations in the subsurface. And these are sometimes referred to as capillary pressure 0, at 0 saturation, 0 NAPL saturation, PC0. And physically, what it represents, you've seen this cartoon before of a grain and a grain, and if this is the oil, then it's the delta P that you have to apply to physically push this through here till it gets on the other side of this pore diameter, in a physical sense. All right, what else? I guess the other thing that we talked about was we also talked about scanning curves. So in other words, if we come down here and we find ourselves at this particular position here by reducing the pressure, and if we increase the pressure of the water around this sample again, then what we think would happen is we'd go up here to get back onto this curve. And then if we went down again, we'd come back down and get on this curve like this. So that we have these hysteretic curves that describe behavior. And you remember that we described this based on the idea that if you have a water drop that sits on a windshield, then the contact angle that exists here is very different from the contact angle that exists at the back. This is what we called theta in a previous day. And so whether it's been wet before or whether it's newly wet means there's a different behavior, and that's why we have this hysteretic behavior that sits in the middle. Perhaps not so important, other than just to realize in overview the rationale for that. And so that's our basic curve that we need to deal with. I suppose the other one thing that we did do is that we could also describe this in terms of a different schedule on the right-hand side. And this was 0.3. And instead of capillary pressures, which we define as this, we could define it in terms of what we referred to as the J function. And we probably will derive this. But the J function is just a non-dimensional parameter which takes the capillary pressure, but then just divides whatever that number is by the interfacial tension of the fluid, the permeability of the reservoir, and the porosity of the reservoir, square root, just as a number. So if you have all these properties and you know what the capillary pressure is on this axis, then you can make this number. And it turns out to be useful to us because it says that always the value of J when this bubbling entry occurs is given by 0.3. And so if we know that this is equal to 0.3 when invasion occurs, then if we know the permeability of our reservoir, its porosity, and we know what the characteristics of the fluids are, we can calculate what the entry pressure is. If we know what the entry pressure is, PC0, so if this is 0, then this would also be 0. If we know PC0, then we also know that this is equal to a height rise times the unit weight of the non-wetting fluid. And so this is this height rise that exists. Not a very good drawing, I don't think, there, but this is HC0. And so it tells us something about the column height that we'd have to get to invade the system. And so what we want to use this for is to say something about the two things we said. One, we want to know when do we invade, and is there anything that stops it from just keeping on invading to the center of the Earth, would be one question. And as it moves through the column and leaves this smear in this column, the chimney as we've called it, as it goes through, what is the variation of saturations within our reservoir? And so that kind of relates to the idea that what we could think of this as is a reservoir where we have a column of this fluid that's sitting there, and it has some height to it, and this is kind of HC, H sub C. Can you see that one there? That's terrible, isn't it? And presumably this has traveled down through here, so it's at less, the pressure is large enough to invade this. But I suppose the question is, how big does HC need to be if it's applying itself onto this little height here for it to keep on going? And clearly it can't go all the way because it's stopped at this particular location. And so that's kind of the idea that we want to be able to apply to understand this, because it intrinsically impinges on the architecture that we'd expect to see in the subsurface. So that's what we're going to do. So anyway, so this is our key curve that we're dealing with. And so I suppose we should make two important points. So many colors on here already. The first one is, if we're interested in figuring out these two things, A is, can we invade? It's interesting, when I look on Google search on invasion of fluids, you get all kinds of different kinds of invasions come up in Google, which you don't want. Can we invade, and what arrests transport? So in other words, if it starts going down, what actually stops it? And I suppose B is what is the distribution of saturation. How are we doing for time? Yeah, we're okay. So that's good. I will just say before we move on that the other thing that we did yesterday on Tuesday was we talked about these capillary pressure curves, and just as a different way of representing them, so our curves look something like this: capillary pressure versus saturation between 1 and 0. And we did actually just transform these by changing it around into these Brooks-Corey curves. So this is what we will call, is it 2 P's? I don't think so. Versus saturation curves. And we also talked about these Brooks-Corey curves, which was just another way of drawing them as log of capillary pressure divided by unit weight of the fluid, because it comes from agricultural, and an effective saturation, which we defined last time. And we noted that effective saturation just truncates this curve as effective saturation going from 0 here to 1 here instead of this scale. And if we do that, we end up with a curve that looks like, bless you, let me do it a bit larger. It would look like this. It linearizes it. And so, actually, so these heights basically are equivalent to each other, not really an arrow. So this is the entry pressure at very low saturations, and it grows. So it's just, and you could flip it around, but it's basically the same curve that takes these same data and notices that if you plot it on a log-log scale, then all of a sudden it conforms to a straight line. And it's useful because then you can describe the capillary pressure saturation curves in terms of very simple relationship. All right, so that was our mandate in this. So let's go back to our notes. Okay, everyone okay so far? So I don't think this outline really says anything about what we're doing today, but this is the idea. It's these two things. One, when does it enter into the system? How far does it go, as one question, and how do we figure out exactly what the architecture might be? So this is the basic idea. You take an analog of a salad dressing, oil and vinegar salad dressing. The oil sits on top of the vinegar, which is water, and the question is, can it ever be the other way around? Can you have the less dense oil sitting on top underneath the water, the more dense water? And the answer is you can. You'd have to pour it very carefully, but it doesn't rest in that position naturally. And the reason is that if you calculate, for instance, the pressures that are existing at this, if you calculate what the pressure, well, let me use a different color. If you calculate what the pressure is that exists in this little box here, it's just going to be equal to the height and the pressure in the top fluid, which will be the non-wetting fluid, right? Oil, is equal to H multiplied by the unit weight of the non-wetting fluid. The pressure just on the other side of that is going to be, H is roughly the same. And if it's right at this interface, if you shrink them so they're both basically the same point, just on the other side is the interface, then H is the same, and the pressures acting against each other are in balance, so that's great. It just sits there, it has no problem. If you take this boundary and you drag it down, you perturb it by some amount, and you do the same calculation, then you get something a little different. One is that the non-wetting fluid pressure now will be the height plus some small delta H multiplied by the unit weight of the fluid that it's in. But the other fluid, which exists below here, this is done the same as it did last time. So I reinstalled the software on my tablet, so it was just fine. And so I don't know why it's crapped out on me again. I'm going to turn it on again. And see if it's restored. Apparently not. Okay, well, we'll just do it by chatting about it. So at this point here, which is immediately under here, then what you could do is you could go down some height through this, then some additional height through this, right? That must be the pressure at that point. And so the pressure at this point, which we can connect directly to this point, they have to be the same because they're on the same horizontal plane, is going to be H times the unit weight of the red fluid plus delta H times the unit weight of the other fluid below it. And so the pressure acting upwards is slightly different from it. And so the idea is that this fluid is less dense. If it's less dense, then this little perturbation delta H will shrink because it'll be pushed up. But if you imagine this being more dense, then the pressure acting in the red fluid at this point, if this is more dense than gamma W, then the pressure here will be larger in the red than it is in the blue. If it's larger in the red than it is in the blue, it'll tend to get deeper, delta will get larger, it'll be even larger, and so the perturbation grows and it just becomes unstable. And so it becomes unstable, then it will just keep on going. So that's basically the idea. So this is in your salad shaker, not a porous medium, but the same principles apply if you're looking at a porous medium. So what we can do then is we can look now at the system where we have a porous medium. You have a barrel that sits on the surface with the water coming all the way to the groundwater table sitting at the surface. And you can do the same analysis. You can go down through this column in this open barrel to calculate the pressure at this point here. And you can look at the pressure in the water immediately below this. And you know that the pressure in the water has to be atmospheric because it's simply connected to atmospheric pressure here. The pressure in the red fluid has to be larger than that because it's got a column sitting above it. And because it's out of balance, you'd expect the column of the red fluid to keep on moving. And physically what's going to happen is that it will keep on moving until the pressure ahead of it in the water is equal to the pressure behind it in the red fluid, and at which case it'll stop. So you can do a very simple calculation to be able to figure out what that is. So it doesn't matter within this fluid that we're in a porous medium. If we're simply connected from the top to this by the red fluid, it's exactly the same as that existing as a column within a swimming pool. That's maybe in a test tube, if you like, in a swimming pool. So we can calculate the pressure at this base merely by the magnitude of the height of this fluid multiplied by its unit weight. We can calculate the pressure in the fluid in the water, again, by the height, the depth of that multiplied by the unit weight of water, and that's the material, the pressure balance at this point. If we equate what those things are, but add on to it this one extra component, and the one extra component I can't draw now because my pen doesn't work, but the one extra component is this entry pressure, right? We said that to be able to push it into this porous medium, we have to get a bubble that goes through the largest pore space, or the pore throat that's there. And so we have to overcome this component of this entry pressure. We can define it as a pressure, or because we've calculated these other things in terms of heights, we can also define it as a height, a capillary height, and we can transfer between them. And so the force balance that we have at this place is just equal to the red fluid pressure acting at this point, which is this. The blue fluid pressure acting at this point here, which is this, which is just the depth of the blue fluid times the unit weight of water plus the entry pressure. This is PC0. This probably should be 0, HC0 here. And if you do the calculations, you end up with the calculation that the minimum height you need to be able to make this move downwards is equal to HC0, I guess this should be a 0 here, divided by the ratio of the unit weights or the densities. And that says that if you have a height of this ganglion that's bigger than this minimum height, then it's big enough to push ahead. And if it's big enough to push ahead and it moves downwards, and if it's anchored at the surface and it's getting deeper, then this is only going to be getting, this real height is only be getting larger. And so if it gets in once, it'll just keep on going and going and going. So basically, we've just shown ourselves that if you introduce this into the subsurface and it's able to move, then it will just extend on downwards through the system. And so if it's able to break through, if this length here is bigger than h min, then it will just keep on going, especially if it's attached to the surface. If the supply at the surface then dries up because you only have a single tank full of, a barrel full of the fluid, then conceivably it could detach. And so long as this individual component here is longer than h min, then it'll keep on going. And it'll keep on going and going. And so until it meets something else. And you could imagine two ways why it would stop. One is that it could hit something here that has a higher entry pressure, has a smaller pore space, and so it can't get in which case it would stop, and maybe it would puddle on this. It would just go on top of it like a puddle on top of this. Or you could imagine, for some reason, as we looked at this this ingrain figure, if I can find it, this idea that as this runs, you see these necks that develop. See, there's a break-off that's occurred, a little necking down. For some reason it's pinched off, and you have a little globule that's gone ahead with maybe oil and water between it and oil. And so if it pinches off, you could imagine that that's one reason by which you could break this one ganglion that we have that exists as one piece into two pieces. And now if these two pieces, either one of them or the other of them is less than h min, it would just stop. And so that's the reason why we could expect that we might see these arresting behaviors in the subsurface. So yeah, so that's really the first thing that we talked about was, when does it mobilize? Well, it mobilizes when the height is greater than the minimum height. And this equation will always allow us to calculate that. And so if we know, for instance, what the height of the fluid would be in the barrel, then we could calculate whether it starts off in the first place or not. So that's one thing. Kind of. But it turns out that there are two equations that we've described that say something about this process. The first one is that if the height is greater than HC0, then an HC0 is related to the bubbling pressure, which we can always calculate. So if the height, this is a physical property of your aquifer, so if the height of the fluid is bigger than this amount, then it can invade at a very low saturation of the non-wetting fluid, right? 100% water saturation, or 99% water saturation, 1% oil saturation. 100% at that particular point, but maybe 1% if you take a bigger REV that goes around it, from what we looked at like this, right? The idea is that in this, it's 100% saturated in the pore space here, it's 100% saturated in the pore space here, but if you draw a box around this, then the saturation really might be only 25%, and that's what we're interested in, even though it fills it down an individual tube. And so, unfortunately, we have two numbers for this. we have this value that we see here, which is HC0, and we have this value that we see here, which is HC0 divided by a number that has to be smaller than 1. So it's larger than HC0. And so why do we have two numbers? And so that's best explained by this little analog here. And it all relates, if you like, to this idea of buoyant weight. So you think of your aquifer as finishing here. This is the ground surface at the bottom. You have your 55-gallon drum sitting on it with a hole in the bottom. And then if you open the drum, then the invasion would occur if the height of this is bigger than this bubbling pressure magnitude. The first one we talked about, the value on the curve. If you raise the water table up to the same height on the outside of the barrel as the level of the oil that sits in the barrel, then this will only invade when it overcomes this minimum height, which is this. And the reason for this is that outside here there's air, and outside here there's water. And so the pressure that's acting on this interface is really the hydrostatic pressure due to this water. So you can think of it almost the idea that this is in this case, the buoyant weight of this fluid is reduced because it's below water. It has buoyancy in it. And so the pressure that's acting this here is reduced over the case where there isn't this water outside. It's like the idea of being something that's submerged below water, actually having a buoyant force pulling it upwards. And so the height that you have to add in this particular case is actually larger than you have to add in this case. And so we're not contradicting ourselves, we're just allowing the fact that there is nuance in terms of behaviors. And so if we're already in the subsurface, so in other words, the only way that the water table's going to be up at this level is probably going to be if the ground level is at this level. I'm trying to draw this from my pad. And so they represent two different physical systems, right? The ground level here and the ground level here. That's what they represent. Okay? So that was one of the things that we said we'd like to figure out. The other one was this, and that is what's the distribution of the saturation. So we know we can get into the subsurface, but what is the architecture, if you like, that we would expect to see as we go into the subsurface? Because this is going to be useful to us because we said before, if we know what the saturations are and what their distributions with depth are, we have a chance to be able to calculate what the mass would be in place. And we could do a couple of things. We could calculate, one, if it dissolves at some rate, how long will it take before it's completely removed? How long will it be in place? The calculation would tell you decades or centuries. Or if you try and flush water across this and try and remove it at some low concentration, again, how long will it take to remove? And so for this, we need to understand something about what the distribution of pressures might be in the subsurface. And we'll use this diagram here. And so this is the idea. And I guess let me try. Geez, I wish I could understand that. Anyway, I can't. I don't have a pen. So the easiest one to understand is this. This is the ground surface. The water table floods the soil all the way up to the ground surface. And what we want to do is we have a denser than water non-aqueous fluid, which is this green phase here, which we'd like to know whether it can invade or not. So what we can do is we can think of these again as a swimming pool. The porous medium doesn't make much difference. We could think of it as a test tube, a swimming pool of the blue fluid, a swimming pool of the green fluid, and calculate what the pressure distribution would be in going from the surface to depth in the swimming pool. If it's in water, we know that the pressure here at the surface is atmospheric. Gauge pressure is 0. If we go down in the water, the pressure will increase at the unit weight of the fluid. See if I can write it. PW will be equal to the depth Z multiplied by, that's a Z, you wouldn't believe it's a Z, but you should believe it's a Z, times the unit weight of the water, right? And so it's just this gradient here that defines that. And if the green fluid is denser than the water, then the gradient of pressure as you go down is more shallow. I guess the pressure builds faster, but this curve, I guess, is, you could say it's more shallow rather than steep. And at any particular point, you can calculate the pressures in either of those fluids just by going down to that particular depth and looking at what that magnitude would be. I deserve a medal for this, I think. This. So this is the pressure at this point, and this would be the pressure at this other point. And so it doesn't really matter whether we're in a porous medium or a swimming pool. The same pressures, if the fluids are static, would apply. Obviously, if you want to know the pressure in the non-wetting fluid, we can do it by the same calculation. Perhaps you can't see that very well. And the other thing that we can do is we can take this capillary pressure versus saturation curve, which we've had before, and flip it. Flip it so it's upside down. So that pressures are increasing from 0 to 100%, 0 pressure to some large number. And then also realize that this magnitude of capillary pressure we've defined in a very specific way, right? We defined it by definition as the pressure between the non-wetting fluid, NW, and the wetting fluid. And so by definition, that magnitude is just this length here on this curve. And so the capillary pressure at the surface, the difference between these two curves is 0 and becomes larger, scales directly with the depth below the surface. So it increases linearly. And so that's exactly the behavior that we have going down. So if instead of plotting the pressure with depth, we plot the capillary pressure with depth on this curve, then we could stretch, you could imagine stretching this capillary pressure versus saturation curve so that the capillary pressures directly match what they would be. So in other words, you know the capillary pressure is here is 0. If you found out the capillary pressure here was 10 pascals, PA, then you'd want to find exactly where on this curve 10 pascals was, and you'd stretch it so that this ordinate was directly level with this. That's it. And then that would tell you something exactly about this particular system. It would say something about the saturations, and that is that as you go progressively deeper in this, that the saturations of the two phases would change. We did it in black before, so let's do it in black again. And that is that at any particular depth, if this happens to be the correct depth here, then we have two components. At this particular depth, this will be the saturation of the non-wetting fluid, and this would be the saturation of water. So in other words, at this point here, it's all water. There's no height at the top to be able to displace the water because you can't push the other fluid in. So we've got to get over that kind of bubbling issue. So this is all water. As soon as we get to this point here, we'd be able to invade it. So somehow we have to get at least down to that distance. And then if we have a connection to the surface that can supply this non-aqueous fluid to depth, then at this particular height here, there'll be a small amount of oil and a big amount of water. At this point here, there'll be a larger amount of oil and a smaller amount of water. And at these ultimate depths here, this will be the largest proportions. And so that immediately allows us to say something about the structure of what this would look like. And it doesn't look so different, I hope, to the behavior that we've seen here, in that if you zoom in on this and you go down, you have some small saturation here, and then when you have this height of capillary pressure above it, you have a high saturation in these lower parts, where you have a big column that's able to saturate it at high saturations, whereas here you saturate it only at relatively low saturations. And so capillary pressure curves, we don't really say anything other than a wetting and a non-wetting fluid. We can choose what those fluids are. Here the wetting fluid is water and the non-wetting fluid is oil, as in these cases. And from that we can use that to calculate what that distribution would be. So, straightforward, I think, right? So in this particular case, we've worked below the groundwater table and we've defined that. So it says what the distribution is. So that's for the case where we have water that's being invaded by a denser than water oil. What happens if it's a lighter than water oil in the system? Anything? If it's lighter than water, it's just going to pond itself on the top. As you go down here, I can't draw it very well. I guess the lighter than water oil would increase in pressure on this side of the water line. It would be less dense than the water, and it would float. So it's the same as oil floating on top of a swimming pool, gasoline floating on top of a swimming pool. It would float. There's no way that it can get down to the bottom. NAPL, put it on the swimming pool, it sinks immediately to the bottom of the pool. And so if it was gasoline, nothing would happen. So this specifically is a oil-water system. Water wet, oil non-wet. If we look at an alternate system, which is an air-water system, again it's just two fluids, not two liquids. One's a gas and one's a liquid. The other ones are both liquids. The water we'll take as being the wetting fluid, and we'll take the air as being the non-wetting fluid. We can do exactly the same thing. In fact, it might be almost more logical, because now the capillary pressure curve, capillary pressure saturation curves look like we've seen it before. It's standing the right way up, as to this one was flipped upside down. And the geometry now that we'll take is a little bit different and is given by this geometry here. So now the ground surface is up here. The water table is still here at the same level at the bottom. Probably in 452 you talked about the vadose zone and the capillary saturated zone. In other words, the zone that is saturated because the surface tension in the water is high enough to pull up the water, just like in a capillary tube. This actual location here is at atmospheric pressure, and this pressure here is less than atmospheric pressure because of the capillary fringe. And above this, it's basically air. So this is filled, pore space filled with air, pore space filled only with water, almost 100% saturated with water. And below this, the saturated groundwater zone, which is also 100% saturated with water. And so we haven't made the case yet that this should be water saturated, but we can rationalize it by what we've said before. If we look at ignoring this line here and looking at how pressure changes from the water table by definition is where the pressure is equal to atmospheric. So the pressure here in the water has to be 0. As you go down, then it has to increase according to the unit weight of water. if you drained out the water and looked at air-filled pores, the pressure in the air would increase as you go down, just because of the height of water above it. Same as the fact that we're at 14.7 psi here, and if you go up to the edge of the atmosphere, you're at 0 absolute pressure. 14.1 bar, 100 kPa absolute pressure at sea level, because of all the air that sits above us, the gas sits above us. And so as you go across this boundary, there's no reason why the pressure changes shouldn't also just keep on going up. And so as you go up here, the pressures go from 0 to progressively more and more negative water pressures, which is really saying that if you want to get up to this point here, you have to be able to hold a column of water up, which is equal to this height. And it's the force you have, the pressure that you have to apply to hold up that column. If you go up in the atmosphere, the pressure decreases much more slowly than it would do in a water column. And for the same reasons as before, the difference between these two pressures, by definition, is the capillary pressure, right? Here the capillary pressure is the difference between the non-wetting fluid minus the wetting fluid. It happens to be the air minus the water pressure. Is that funny? Is that you too? Is it a good you too? And as you go up through this, this is negative. So a negative to the negative is a positive, and this is a small number. This is basically 0. So capillary pressure, this would be a positive capillary pressure, as indeed these should be. And as you go up to some height here, the capillary pressure will be small enough that you can't push a bubble of air into the system. But as you go above this, then all of a sudden you can push a bubble of air. And so the saturation then would be, again, the saturation of the non-wetting fluid. And again, the saturation of the wetting fluid. And so progressively, it really describes this geometry that we have. So up to this point here, the saturation of water is 100%. And this conforms to what we know about this being the capillary fringe, or the tension saturated zone. It's 100% saturated with water, no air in it. Once you get above the top of this, progressively you get proportionally more and more air in the system and less water on the system. Individually, at different stages here, this would be, in terms of our comments of pendular and funicular saturation, I guess it's always interesting this would be almost fully water saturated, so this would be funicular saturation, and this would be pendular saturation as you go here in terms of our definitions. And so if we wanted to, and it will be perhaps your third assignment, is to calculate what the saturation can be in a subsurface system for a NAPL when you use the Buckley-Leverett curves to be able to do that. And that's probably it. I'm trying to think what else there is. Oh, there are a couple of things. So I think we talked about the apparatus last time. So that is it, I suppose. So some data here. The only other one thing to look at while we're here. Your assignments have been dealing with transport of some advected radionuclide component from Yucca Mountain to Long Street in the saturated groundwater zone that exists below the repository. And so the potential Yucca Mountain repository sits on the Nevada test site, 100 kilometers from northwest of Vegas. Ground surface, potential repository maybe 300 meters below, groundwater table roughly 600 meters below. And below the groundwater table, it's water saturated. And this is a cross-section of a whole bunch of experimental data points on that section. So 600 meters is something like 1,800 feet, right? 3 times 600 is 1,800. This is the ground surface. This is the water table. And this is the capillary potential that's in the water as you go down through the column. These individual, it's a really scrappy diagram, but you get the picture. Each one of these dots is a data point. One sample, one core sample, which has been tested to measure the pressure within the water. There's lots of air pressure within those samples, mainly air, but the water is present at some low saturation. And this solid curve here is, or the dashed curve rather, is the hydrostat. So it's just the unit weight of water multiplied by the height above the water table, 0 at the water table, plus 600 meters above it. And this is 1 atmosphere, 10 atmospheres, 100 atmospheres, 100 times atmospheric pressure. And this is the curve that says the theory. Physically what this means is if you went up to this, the surface here, and you took a column of water which was 600 meters tall, and you tried to hold on to it as it goes down into the ground 600 meters, and instead of pulling up on it, you applied a suction pressure so you could actually hold it there. The suction that you'd have to apply would be this pressure here. Roughly, what is it, 50 bars? I'm not sure. You can calculate it out, right? Yeah, easy to calculate. And so as you go down, if you cut that column below you by to 300 meters, then it would be this. If you cut that column right at the water table, the height will be 0, and so the pressure will be 0 bars. It's a log scale, so you can't see that. So these are the data points for the pressures that are in the system, and they conform reasonably well to the theoretical maximum value, which is the height of the water column that you're supporting to do this. Because these pressures are so low, what would you expect these to look like? So these capillary pressures are really high, and so you'd expect there to be a really high gas saturation and a very low water saturation, and these would are really low capillary pressures, so you'd expect it to be water saturated. So as you went down this is not defined in terms of saturations, but it's determined in terms of water pressures. The capillary pressure curves for the different units, 2 of the different units are shown here. 100% water saturated, some pressure, 0% water saturated, a much larger pressure. This would be the this would be the water saturation. If I draw it across here, black's no good, is it? This would be the water saturation. Saturation going across here. And this would be the air saturation, which is bubbling in and trying to get into the pore space. And so we've tried to make the case that these capillary pressure versus saturation curves are the key to basically understanding the architecture that we have in the subsurface. The saturation architecture in terms of 2 fluids, one of which is water and one of which is air, which basically conforms to this behavior that we've tried to describe here. And because we don't necessarily say anything about the fluids other than the fact that they're wetting or non-wetting, we can exchange air and water just as easily for NAPL and water and turn it upside down, and exactly the same processes endure. So we're probably 10 minutes short. That's fine. Any questions? What we talked about? Okay. Oh, you're very compliant and quiet. So everything we've talked about today has been about the static behavior. I guess this figure. Turn up on its side, freeze the motion. This is the saturation and its distribution in the subsurface. What we'll start talking about next time is what happens, how do we calculate the rates at which this movement will occur? And for that we need to say something about permeabilities, relative permeabilities. So next time we'll start talking about multiphase fluid transport rather than just this equilibrium behavior.